In this video, we're going to use our old method for finding the Taylor series by equating derivatives to find the basic Taylor series for ln of x, centered on x equals 1. Now, for all of the other basic ones, e to the x, sine of x, cosine of x, we've used the Maclaurin series. We've centered on x equals 0. Why don't I want to do that for ln of x also? Why do I have to be different? Well, if you think for a very quick minute about what ln of x looks like, based on everything we know from Algebra 2 and Pre-Calc, you can see you can't center a graph on x equals 0 if the graph doesn't exist at x equals 0. So we're going to pick a spot where the graph does exist and use that instead. But other than that, the process is exactly the same. We're going to find the derivatives at all levels of ln of x, evaluate them all at that a where we're centered on, which in this case is 1, and then use those values to find the coefficients and just put them into a polynomial and see if we can recognize the pattern. I promise this pattern will be a lot easier to spot than the last one. So let's go through that process again, and remember, if I go a little bit too fast for you, feel free to pause me and catch up on your own. In fact, you can probably do this on your own and then just fast forward the video to make sure you did it right. So let's start with the function and a bunch of derivatives. We're not going to need as many here as we did in the last case. So we'll start with f of x, the function that we're trying to expand, and then find its derivative and its second derivative. Remember, we can use the power rule to take the derivative of that 1 over x, bring down the coefficient, and lower the exponent from -1 to -2. And we can find the third derivative, and if we need to, we can always come back later and go beyond this, but I think 3 derivatives should probably be enough for us. For this one, we will bring down the 2, really bring down the -2, which cancels out the negative sign. It also makes the coefficient be 2, and lower that exponent from -2 to -3. If we need more, we'll come back and do more later, but I think that should be enough. We're going to evaluate all of these at 1. We know the ln of 1 is 0. We know 1 over 1 is 1. -1 over 1 is -1. And 2 over 1 cubed is 2. So that's enough. We see that the signs are alternating. Because remember, 0 could be -0 if we want it to be. And we see that, well, you know what, I'm going to do one more. The fourth derivative, it'll only take a second. Bring down the -3 and make that x to the 4th. So the fourth derivative here, evaluate that at 1, would be -6. Okay. Doesn't look like there's a discernible pattern there, but we'll see. When we find our coefficients, our C0, C1, remember C0 is equal to f of a, C1 is equal to f prime of a, C2 is equal to f double prime of a over 2 factorial, C3 is equal to f triple prime of 3 over 3 factorial. I'm going to write the 3 factorial like that. You'll see why in a second. And C4 would be f, the fourth derivative of f of a, over 4 factorial, which I'm going to write as 4 times 3 times 2. I'm going to write the factorial out, and you'll see why in a second. Notice, of course, we can do some simplifying here. So that's still 0, 1. These can't get simplified. We, of course, can simplify these, but I want you to see the pattern and what's going to happen when we simplify. The 2 over 3 times 2. Of course, the 2's cancel. We're left with 1/3. The 6 over 4 times 3 times 2. Notice that this numerator up here, I didn't write it out, but this really came from taking, remember, it was 3 times 2. That's where it came from. And that's the same 3 times 2 as that. So those are going to cancel out. And we're left with negative 1/4. And that's going to keep happening. The C5 would end up being 4 factorial in the numerator. You can see how these are all one step behind. These are all one step behind, meaning that the 4th derivative had a 3 factorial in the numerator. The 3rd derivative had a 2 factorial in the numerator, and so on. So this is 4 factorial over 5 factorial, which is really 5 times 4 factorial. And so the 4 factorials will cancel out. And that pattern is going to keep going. It'll be 0, 1, and then 1/2, 1/3, 1/4, 1/5, of course with the alternating signs also. So we can identify that pattern that we've just described. The sum of our coefficients, it's first of all alternating. And then also we can say that it is, we see the x minus 1 to the nth factorial, because we see that these terms are going to have, we're not skipping, we're not counting just the evens or just the odds like with a sine or with the cosine. We're going to count every term here. There were no zeros, nothing got canceled out. And then the denominator of that coefficient is not n factorial, it's just n. There's one catch here. If I'm putting n in the denominator, I can't start with 0, which means I'm going to need to start with 1 and go from there into infinity. And because of that, there's also one other tiny little catch here that we've got to be careful about. My alternating term here, the alternating sign, I don't start with negative 1 to the nth anymore. Because if I'm starting when n equals 1, that wouldn't be negative 1 to the first. That would start with a negative number. But we can see my first term is not negative. So I'm going to need to either do plus 1 or minus 1 here, so that I realize it is a negative term. It is an alternating sign, but it's starting, making sure I'm starting with a positive number. And if we just follow this pattern, we'll see that it matches the coefficients we did in pink. The first term when n is 1 will be negative 1 to the 2nd power, so that's positive, over n. That's just a 1, times x minus 1. Right, there's that 1 there, which we just figured out. The next term is negative, because it's negative 1 to the 3rd, so we're up to the negative term, over 2 times x minus 1 to the 2nd. And that matches this times x minus 1 to the 2nd. And the next one will be 1/3 times x minus 1 to the 3rd, and so on. And so that is the Taylor series for ln of x.